Hello and welcome to another chemistry video, this being part 2 of a two-parter on limiting reactants. We'll start with the Nevada State Science Content Standard. It says that students know that in chemical reactions, elements combine in predictable ratios and the numbers of atoms of each element do not change. Our objective: upon completion of instruction, students will be able to calculate the amount of excess reactant after a reaction has occurred. In our last video, we spent most of our time determining limiting reactants and how much product could be made. We introduced the concept of excess reactant, and in this video we're going to cover those same things, but we're going to spend a little bit more time on excess reactant. Okay, so given the following balanced equation, aluminum sulfate reacting with sodium hydroxide, producing sodium sulfate and aluminum hydroxide, our situation where we put in 12 grams of aluminum sulfate and it reacts with 15 grams of sodium hydroxide, our two reactants. These are going to react until one of them is gone, making the one that disappears be the limiting reactant. It limits the reaction. As soon as one of these is gone, it's reaction time over. So to figure that out, we do a couple stoichiometry problems. We start our first stoichiometry problem with 12 grams of aluminum sulfate, as it says right here, and we're going to go to one of these two products. It doesn't matter which one as long as we use the same one for both equations. Looking down here at number B, we can save ourselves a little work because we're going to have to find how many moles of aluminum hydroxide are produced. So why don't we go from grams of each of these to moles of aluminum hydroxide, because we're going to have to do it anyway. So 12 grams of aluminum sulfate. The first thing we're going to have to do is convert that to moles. Grams to moles means simple unit conversion. 1 mole of aluminum sulfate is equal to the molar mass of aluminum sulfate. Now that we've converted to moles, we can do our mole to mole ratio. Moles of aluminum sulfate to moles of aluminum. 2 moles of aluminum hydroxide for every 1 mole of aluminum sulfate. And our stoichiometry problem is complete. It's got us 2 moles of aluminum hydroxide, which is what we want. So we push the buttons on the calculator and it magically spits out 0.082 moles. Okay, now let's do the same thing with sodium hydroxide, our other reactant. It says we've put in 15 grams. And again, we have to do a conversion from grams to moles because we want moles. 1 mole of sodium hydroxide equivalent to 40 grams, the molar mass of sodium hydroxide. So now we're at moles, and now we can do our mole to mole ratio. 6 moles of sodium hydroxide, 2 moles of aluminum hydroxide. Looks like that. Stoichiometry problem complete. Push buttons on your calculator, little magic, come up with 0.25 moles of aluminum hydroxide. The product that runs out first, the reactant that runs out first is aluminum sulfate because it can only make this much aluminum hydroxide and then it's gone. So we'll never be able to make this much because the aluminum sulfate runs out. So our answer for A, aluminum sulfate makes less product, so it is the limiting reactant. Okay, let's move on to B. Oh, guess what? We already did B, didn't we? We know that this is the amount. The limiting reactant tells us how much product can be made. So B is done. Oh man, don't you love it? Life is so easy. Okay, for C, we have to determine the number of grams of sodium sulfate. Okay, now this sounds like a whole lot of do this stuff all over again, 2 problems, but think for a minute before you start. We know that the limiting reactant is the reactant that will determine how much of each product can be made. So really, we only need to do one stoichiometry problem to find the answer to C, because we know what the limiting reactant is, aluminum sulfate. So if we go from 12 grams of aluminum sulfate to grams of sodium sulfate, we'll have our answer. Okay, so that's as simple as 12 grams of aluminum sulfate, conversion to moles. So now we have moles of aluminum sulfate, our mole to mole ratio. We have 3 moles of aluminum sulfate for every 1 mole of aluminum, 3 moles of sodium sulfate for every 1 mole of aluminum sulfate. So that's our mole to mole ratio. And now that we're at moles, we have one thing left to do. We have to find grams of sodium sulfate. So we go from moles of sodium sulfate to grams, simple unit conversion. Looks like that. 1 mole of sodium sulfate is equivalent to the molar mass of sodium sulfate. Push buttons on your calculator, and you should get 23.27 grams of sodium sulfate produced, which is where our reactant runs out and we can't make any more. Okay, for D, we need to determine the number of grams of excess reactant left over in the reaction. Okay, now the way you do this is you take the amount of product that was made, and it doesn't matter if you use grams of sodium sulfate or moles of aluminum hydroxide. Either product, either product, you've calculated both of them, moles of one, grams of the other. Either one, doesn't matter. You're going to go from how much of either one of these was produced back to the excess reactant. Sodium hydroxide is the excess. And if we go from how much of these was made to back to this, we're finding out how much of it was used in the reaction. Once we know how much was used, we'll be able to subtract it from what we started with, 15. So first let's do stoichiometry from one of these. Moles is a little bit easier. It's one step shorter. So let's go from moles of aluminum hydroxide back to grams, and we have to go to grams because we're given grams to start with. So moles of aluminum hydroxide to grams of sodium hydroxide. Okay, so here we have our moles of aluminum hydroxide, and we can go straight to our mole to mole ratio. For every 2 moles of aluminum hydroxide, we have 6 moles of sodium hydroxide. And again, that has to do with the coefficient, 2 moles of aluminum hydroxide, 6 moles sodium hydroxide. Okay, that's our mole to mole ratio. Now we need grams of sodium hydroxide. So what we're going to do is our unit conversion again. 1 mole of sodium hydroxide, and over that will be the molar mass, 40 grams of sodium hydroxide. Push buttons on your calculator. This will tell you how much reactant was used, and we've used 9.84 grams of sodium hydroxide. Now, we're not quite done yet. What we have to do next is subtract that 9.84 from what we started with, and we started with 15. So 9.84 or excuse me, 15. Well, I need some color here. Here we go. 15 grams, and you're going to subtract 9.84 grams, and that will tell us how much is left over. And you should come up with 5.16 grams of sodium hydroxide excess or leftover, however you want to say it. Okay, so there's actually a couple of steps to finding how much excess reactant is left. First step, find how much was used. Second step, subtract it from what you started with. Okay, at the start, I can spell start. We had this much, and over here, and we subtract it from what was used. Okay, seems simple enough. Let's try another one. We'll work through a few of these. Okay, the following reaction, again, we have a balanced equation. And you can read through this. We're going to assume that we put in 30 grams of ammonium nitrate, and it combines with 50 grams of sodium phosphate. Okay, we're going to determine which of these is the limiting reactant. And then in B, we're going to determine the maximum amount of each product that can be formed. And we know that that is determined by the limiting reactant, because once the limiting reactant is gone, we can't make any more products. Okay, and we're going to determine how much of the other reactant is left over, how much is excess after the reaction is complete. Okay, so first, which is the limiting reactant? We have 30 grams of ammonium nitrate. Our conversion to moles, 1 mole equivalent to the molar mass of ammonium nitrate. Our mole to mole ratio, 3 moles of ammonium nitrate for every 1 mole of ammonium phosphate. 3 subscript, no subscript here, and pushing buttons on a calculator, we get 0.1249 moles of ammonium phosphate can be formed. Okay, and our other stoichiometry problem for A, finding the limiting reactant, we put in 50 grams of sodium phosphate, and we do our conversion to moles, 1 mole of sodium phosphate, equivalent to the molar mass of sodium phosphate. And then we do our mole to mole ratio, and there's only 1 mole for each of those, so it doesn't really factor in math-wise. But this would be able to produce 0.305 moles if it were the limiting reactant. However, this being the smaller answer, we know that our limiting reactant is ammonium nitrate. Okay, and since you know how to find the products now, you know that the limiting reactant is what determines how much product. You can simply, this one you've already calculated, how much ammonium phosphate can be produced. And you can do the stoichiometry problem and see if you come up with this answer. 0.3748 moles of sodium nitrate. Okay, moving on to C. How much of the other reactant is left over, excess, after the reaction is complete? Now again, you know how much of each of these products is produced. You know this to be the excess reactant, the reactant with leftovers. So you're going to convert from either one of these back to how many grams of sodium phosphate was used. Once you have how much was used, you subtract it from the 50 grams you started with. So we have 0.1249 moles of ammonium phosphate. We do our mole to mole ratio because there was 1 mole of each in the equation. 1 mole here, 1 mole there. So that really doesn't affect anything math-wise. Okay, and you do your unit conversion to grams of sodium phosphate, molar mass over 1 mole. Pushing buttons on a calculator, you have 20.476 grams of sodium phosphate were used in the reaction. And finally, we subtract how much was used from the 50 grams that we started with. Remember back up here in our word problem, it said 50 grams of sodium phosphate was what we started with. So we subtract reactant at the start, 50 grams, reactant used, you just calculated that. You subtract these, you get 29.52 grams of sodium phosphate excess. Okay, here we have another problem. Consider the following reaction. I'm going to zip through this one a little bit faster because by now you should be catching on to these and you can stop the video at any point. Okay, so the following, got a balanced equation. We're putting in 100 grams of calcium carbonate with 45 grams of iron phosphate. These are our two reactants. Which reactant is the limiting reactant? Again, two stoichiometry problems starting with these two amounts of reactants that are put in. Okay, the amount put in, conversion to moles, 1 mole over the molar mass, our mole to mole ratio, just as you can see up here, and pushing buttons on a calculator, you get this for an answer. And our second stoichiometry problem to figure out A, 45 grams of iron phosphate, just says iron phosphate, our conversion to moles, and our mole to mole ratio. We found calcium phosphate for both of these. And it looks like all we can make is 0.149 moles of calcium phosphate because that's when the iron phosphate runs out. Therefore, we know it to be the limiting reactant. Makes less product, makes it the limiting reactant. Maximum amount of each product that can be formed. Well, we just found one of those, didn't we? 0.149 moles of calcium phosphate. To find the other one, you're going to go from this limiting reactant, the 45 grams, to the other product, which is iron carbonate. And you get the same amount, which may seem strange, but the reason for them both being exactly the same is, look at the mole ratios. You're going from iron phosphate to, we have 2 moles of iron phosphate, 1 mole calcium phosphate, 1 mole iron carbonate. So the mole-to-mole ratios end up being the same, and since you're putting in the same amount both times, this first part of the equation stays exactly the same. And in fact, everything's the same except for the chemical formula, of course. So that's why those end up being both the same. Okay, finally, C. How much of the other reactant is left over after the reaction is complete? We go from the 0.149 moles of product, either product, it doesn't really matter, do our mole to mole conversion, and then convert to grams of the excess product. The calcium carbonate was our excess because it could have made more. So this tells us how much was used, and we're going to subtract that from what we started with, 100 grams, subtracting 44.497, and we get an excess of 55.203 grams of calcium carbonate. All right, I think we have time for one last problem, and then we're going to call it quits. So we have our balanced equation. We have how much of each reactant we put in, of silicon, hydrogen, and some oxygen, and we're going to find out what the limiting reactant is, how many moles of silicon oxide. So again, here's a tip-off on which one you'd probably want to go to, since you have to find it anyway. And then we'll find our excess reactant. So again, we're starting with 17.8 grams of one reactant. Convert to moles. We do our mole to mole conversion. 4 of these for every 8 of these. And finally, pushing buttons on the calculator, that would make 6.601 moles of silicon oxide. Our other reactant, conversion to moles, 1 mole equivalent to the molar mass. We do our mole to mole ratio, 11 oxygens for every 8 silicon oxides. Pushing buttons on a calculator, we'd be able to make 6.45 moles. This is our limiting reactant because it makes less. Okay, how many moles of silicon oxide are produced? Well, you just figured that out. We're going to find the excess, the amount of excess reactant. So we're going to start with the amount of product we could make and work backwards to the reactant that would have excess, which is oxygen. And we'll find out how much was used. 0.601 moles. We do our mole to mole ratio. We have 8 moles for every 11 moles. It's our mole to mole ratio. And Moles of oxygen top, moles of oxygen bottom. 1 mole is equivalent to the molar mass of O2. And we have 26.44 grams of it used in our reaction. We started with 28.4, so we do a simple subtraction problem, and we find that we have 1.957 grams of oxygen left over. Okay, that's it for limiting reactants. I hope this helped you. Thanks for watching.